Hello, everyone. Thank you for joining in today's webinar series. Welcome to this week's SED Online webinar. As always, we'd like to thank our sponsorships from IAS, which allows us to offer all of the resources free of charge for these webinars. This includes not only the webinars, but all recorded lectures, learning tools, and even some virtual field trips. So go ahead and take a look at the website to see all the new information that is available. Today's lecture is by Dr. Nora Nofke, who's an associate professor for geobiology at Old Dominion University in Virginia. Nora received her bachelor's and master's degrees from the University of Tübingen before attending the University of Oldenburg for her PhD. Dr. Nofke is a sedimentologist who has helped establish the scientific field of biofilms in clastic sedimentology, and her research is highly interdisciplinary, combining sedimentology with microbiology, geochemistry, and mineralogy. So thank you for joining us today, and welcome, Dr. Nofke, and with that, I will pass the mic on to you.
All right, yeah, thank you very much for everybody to be here, and Kim and team for organizing this really interesting seminar series. So my turn today, the topic of my talk is a microbial ecosystem in the 3.48 billion year old Dresser Formation in the Pilbara Block, Western Australia. That's a study I conducted a few years ago in collaboration with Bob Hazen from the Carnegie Institution in Washington, DC, and also David Wasey at the University of Western Australia in Perth. So first of all, I like to make very clear that I'm not going to talk about stromatolites here. I'm going to talk about a group of sedimentary structures which are called microbially induced sedimentary structures, abbreviated as MISS. Those are structures formed by microbenthos in clastic deposits, so not in carbonates, in clastic deposits. Here is a photo of multi-directed ripple marks. A knife for scale about 20 centimeters long. Here you see a patch of ripple marks, which is elevated. This patch here is overgrown by microbenthos. And here you see ripple marks. They have a different direction. They are in an area that's a little bit deeper. So that's just one example for an MISS. And I'm going to show more in a few moments. So if we take a look here at this photo, we get the impression, well, this is just sand that composes this modern sediment. However, if we take a magnifier, we see actually microbenthos is all over the place. There are two main modern groups of microbes, and especially important are the cyanobacteria. Important from a geological point of view, as you will see in a few moments. So this is here Merismopedia punctata. It is a coccoid species that form round-shaped cells, and they form clusters, pillow-like clusters that are attached to the substrate with their extracellular polymeric substances, which are very adhesive mucilages. This here is a filamentous species here, Microcoleus tonoplastis, was recently renamed. That is a very large microorganism, about 500 microns long, and occurs worldwide. Now, that is actually the microbe why cyanobacteria sometimes are called blue algae or blue-green algae, because formerly people believed those organisms are algae. They are not bacteria, but in the meantime, we know they are actually bacteria. So initially, such cyanobacteria, like all microbenthos in an aquatic setting, colonizes individual sedimentary grains as biofilm. So here you see the surface of a quartz grain here. And you see how this quartz grain is enveloped completely by this organic film. Here we scratch this film off the quartz grain a little bit. So here, those organic films are called biofilms, and they are composed by the individual microorganisms themselves. This is an example for a diatom, plus their extracellular polymeric substances, which are those adhesive mucilages that those microbes secrete. If such biofilms continue to grow at sites where the ecological conditions are suitable, microbial mats develop. That is a photo of a modern microbial mat here. Here's a knife for scale. You see here the clastic sediment. So microbial mat are dense organic layers. This is about 1 centimeter thick, very, very coherent. If you see something like that in the field, it's very common actually. You can bend down, you can grab that microbial mat, you can lift it off its substrate, you can roll it up like a carpet, put it on your shoulder and walk away with it if you so wish. So they are very, very coherent and very large microbial communities. Now, microbial mats interact with sedimentary dynamics in certain ways. If we are in a chemical setting, like a carbonate setting, stromatolites form. We know those are very common. If we are in a physical sedimentary setting, MISS form. And I'm going to talk about the processes of formation in a few moments. So I like just to show you a couple of examples for microbially induced sedimentary structures. Here are those multi-directional ripple marks that I showed in the beginning. Here is a very similar multi-directional ripple pattern preserved in the Pongola supergroup, about 2.9 billion years old. You do not really see the ripple marks too well on the smaller photo here. Such a ripple pattern rises from interaction of microbial mats with episodic storm events. Polygonal oscillation cracks, I will talk about those in a few minutes from now once more. It's a pattern of polygons separated by cracks. So here a modern example that's about 25 centimeters in diameter here. You can see here those rims, those ridges on both sides of the cracks that define those individual polygons. And this here is a fossil example again from the Pongola supergroup here. So here you see those two rims here, and here is one of the polygons. Here is another polygon. Beautiful, preserved in this outcrop in South Africa. Here, erosional remnants and pockets, a view into the modern field. That's the North Sea area, here. The scale here about 1 meter. You see that the sedimentary surface is composed of two structural elements, elevated surface parts which are planar, and deeper lying surface areas which are here filled with water. Those erosion remnants and pockets rise by partial erosion of a microbial mat. Here is a fossil example. The rock bed obviously is tectonically tilted a little bit. This here is the microbial mat surface here. And here you see erosional pockets. That is actually, was originally the sand that is underneath the microbial mat, and it's of course ripple marked. So here those are windows into that show the substrate beneath the microbial mat. So that's an erosional pocket here. Those are erosional remnants. Microbial mat chips are fragments of microbial mat. Here a modern accumulation of those mat chips, and here a fossil one from the Pongola supergroup, again from South Africa. So those were just a few examples for MISS to show you that really those structures look completely different than stromatolites, and we will see they also have a slightly different mode of formation. So clastic sedimentary systems are governed by physical sediment dynamics. That includes erosion, deposition, and deformation. Any microbenthos that colonizes a sandy substrate in an aquatic setting, of course, must be able to respond to erosion, deposition, and deformation. Otherwise, survival would not be possible. And we investigated how cyanobacteria respond to different sediment dynamics and came up with this graph. It looks very complicated, but I'm going to walk you through this very quickly. So this graph consists of 3 arrows. This arrow here indicates the intensity of erosion. This arrow here indicates intensity of deposition. And this arrow here indicates the increase of latency, which is the time period in between 2 sedimentological events, let's say erosion or deposition. So it is a time period when nothing happens with the sedimentary surface. It's quiet. Those rectangles document how cyanobacteria respond to very specific, defined sedimentary conditions. So let's take a look at this. What happens during latency? What happens if the the surface is quiet? We can observe 2 things. One is binding, the other one is growth. This here is a vertical section through a microbial mat, looked at under the microscope, obviously. Here you see filaments. It's a fossil example, but it doesn't matter. The modern looks just quite the same. So here the dark lines, those are filaments, and you see they are entangled. They form this typical mat fabrics. It looks like a carpet. There's some sediment in between. Now the question is, how do cyanobacteria form such a microbial mat fabrics? So microbes have the ability to communicate with each other. We call that cell-cell communication, quorum sensing. So the microbes tell each other where does which filament go. So they move actively through the sediment and they arrange this very sophisticated microbial mat fabrics. Each microorganism is placed at a location which enables it to function best, interacting with all other members of this community, of this biofilm, of this microbial mat. So this active motion, the cell-cell communication, that is what we call binding. There's no growth at all involved. Growth is what we see down here. This is a vertical section through a tidal flat sediment here, very dark because it's rich in organic matter. This is the surface of a microbial mat here. Here we see the ripple marks. Here, that's a ripple valley here, ripple crest, ripple valley, and we see how the microbial mat fills in the ripple valley, and that's of course by biomass enrichment, cell replication, EPS production, so that is growth. Now, various latencies cause different types of colonization. So in areas where there's a constant reworking of sediments taking place, only biofilms form. If there are a few hours time, let's say in an upper intertidal zone, somewhere in a tidal flat, endobenthic microbial mats might form, or in the lower subtertidal zone where there may be like 2 weeks time in between flooding events, we get epibenthic microbial mats. So there are different types of colonization in the context of latencies. What happens during erosion? This is shown here in this photo. It's a microbial mat in the lab. This is a lateral view onto a microbial mat. here, and here is a current passing this microbial mat. Here you see filaments interweaving sand grains. Actually, you do not see the sand grains at all because they are embedded in this microbial mat fabrics. And you might think, I do not really see those filaments. They're out of focus. The reason is that the filaments are embedded in those EPS. The EPS are cohesive and glue those sedimentary grains together. The filaments entangle the sedimentary grains, and both effects increase the resistance of the sedimentary surface against erosion dramatically. And depending on what type of microbial mat, what type of biofilm is colonizing a sediment, we distinguish different types of biostabilization. Now, what happens during deposition of sediment? What happens if there's literally a rain of grains falling down onto a microbial mat? So this here is the same microbial mat that you've just seen when I was talking about biostabilization. Here you see grains raining down onto the microbial mat surface. I just sketched them a little bit so you see them better. What you see is that the filaments orientate themselves vertically and they reach into the supernatant water. What happens is that the grains arrive on the surface of the microbial mat, the filaments migrate around them and incorporate the grains into the microbial mat fabrics over time. So that's called baffling and trapping. And we observe this only, of course, if there is sediment deposited. Now, all those interactions of the microorganisms, of the biofilms, of the microbial mats with the sediment leaves traces in the sediment behind. Think of a worm moving through sand. A worm leaves a trace behind. That trace can become fossil, and then we call it trace fossil. The same is with those microbially induced sedimentary structures, the MISS. So those microbial mats or biofilms cause a trace in the sand. It becomes fossil, then we have a fossil MISS. So we know of them in the modern as well as the fossil, and there are different types. Now this is a summary of the structures we know so far. Here structures that are caused by growth, here structures caused by binding. Those are made by baffling and trapping, and here those are made by biostabilization. Those here in the center are made by an interaction of the microbenthos with different types, by different activities. So here erosional remnants and pockets, again a photo, but this is a meter scale here. Here you see nicely the erosional pockets, here the erosional remnants again. Then we have microbial mat chips. That's a fossil example here from the Cretaceous Dakota sandstone in Colorado in the US. This here is a modern counterpart, very typical, those lobes and embayments and those holes that occur. Then polygonal oscillation cracks, I mentioned those before. Here you see those polygons, here is one, here is one, and those polygons are separated by cracks. The cracks are lined by two rims on both sides. Here the fossil example that I showed you earlier. So how do those structures rise here? So a microbial mat, if it's desiccating during the summer, for instance, those polygons shrink and those cracks are expanding. When the climate becomes humid again, those polygons expand again, the cracks become narrower, and if we have this pattern of repetition, then we basically see that those cracks close and open, and so forth. So we call those polygonal oscillation cracks very, very characteristic MISS. Wrinkle structures, very popular in the literature if people study fossil material. Very, very common MISS characterized by or various types of crinkled pattern. They rise actually by a variety of mechanisms. So wrinkle structures, then here a lateral view on a microbial mat surface. Some microbial mat types may form tufts at their surfaces, which are bundles of where filaments basically grow upward along each other like this. And form those triangle-shaped little elevations, just a few millimeters high tufts. So just that you see a couple more of MISS examples. So how and where are MISS distributed? Now, with respect to Earth history, we know those structures from the Archean to today. This is written in German here. That's good for you. You can learn a little bit German here. So Archaicum is Archean. So we know them from the early Archean, and those structures occur through the entire Earth history until today. And conveniently, we can observe today in the modern how they form, and then we can understand the ancient microbenthos, but also the Paleoenvironment during which those structures formed. So MISS occur everywhere where there are aquatic clastic deposits, so not only in the ocean or on tidal flats, but also along rivers, in lakes, in lagoons. We know them in lakes in the polar zone or even in the high mountains, in deserts where there is a little bit of water, like in Chile, for instance, in the Andes, and so forth and so forth. So they're very, very widely distributed, actually more wider than modern stromatolites. Let's go to Australia. So the Pilbara Block is located in Western Australia. It is an Archean craton, or part of an Archean craton, and part of it is a circular tectonic structure, which is called the North Pole Dome. The Dresser Formation is located here and forms also this circular arrangement here. So Dresser Formation, here it is. It has an age of 3.48. I've written here 3.49, so it's 3.48 plus or minus billion years old. And it is part of the very famous Varavuna group, where since a long time, scientists describe some of the oldest fossils and stromatolites in Earth history. So here it is, Dresser Formation. Now, if we map the Dresser Formation, and of course many scientists have done that, one can reconstruct the following Paleoenvironment. So there's an ocean, and it was separated from the land by a shoal bar, which included ooit, so that was carbonate here. Then there was a tidal flat, probably just microtidal, the tidal range. So the morphology was very, very steep. But we can distinguish tidal channels here, tidal channels where water was moving during the flood and ebb tide. There were stromatolites situated in here. Then there was a sandy intertidal flat, so sandy intertidal areas everywhere here, with tidal pools that included water for a longer time during the day. So here the intertidal, and then here the subratidal, the upper subratidal in this case, areas where there are evaporites, and they were flooded only on occasion. So that is the paleogeographic situation, and we found, as I said before, stromatolites in the tidal channels and microbial mats colonizing specifically those sandy intertidal flats and parts of those upper subtidal areas. That is an example actually from the modern. So that's how we have to think of how the situation has been. So thicker microbial mats in tidal pools. This is the intertidal flat area. Here are some tidal channels. And here there's the somewhat higher areas here where there are evaporites forming. And this is just flooded once in a while. So here, this is the intertidal, where most of the action takes place. So let's take a look. The subtidal zone in the Dresser Formation. This is how those stromatolites look like, very small, just a few centimeters in diameter, very simple in shape. They look like little cones. Also in the subtidal zone, if we take a look at those channel fills, we see ripple marks. So this is a ripple crest here, ripple slope. Here would be the ripple valley. And we see that the ripple slope was overgrown by a biofilm. That's this dark line here. We also see that the ripple valley, which would be here, was filled in by sediment. So here, this is sediment, this white colored part. It was overgrown by a biofilm. Then a fresh layer of sediment was deposited, was overgrown again by biofilm. Fresh layer of sediment, biofilm again, and so forth and so forth. So this ripple valley here was filled in. So if a ripple valley is overgrown by biofilm, we call that sinoidal structure. We see that in the fossil, as you can see here quite nicely. And we took a look at the biofilm itself. So Bob Hayes and David Wasey, they did analysis. So here, that's a close-up. That's how this biofilm looks like. Dave and Bob found carbon in here. It's biological carbon accumulated within one of those little tufts here, or a pyrite, which has an organic sulfur isotope signal. So let's take a look at erosion, remnant, and pockets once more. That's a modern example here. And I would like you to take a look here at one of those fringed margins here. That's where microbial mat is hanging down. This is the erosional pocket here, because I like to show you the same in the fossil in a moment. Here again, as a reminder, those are microbial mat chips here, fragment of microbial mat, and this is something we see in the Dresser Formation. So here we look down onto microbial mat. That's a fossil microbial mat here. Right? This is a fossil microbial mat. The surface, this is the edge of the microbial mat here. It hangs down. This is the former sand, which was beneath the microbial mat. Here it's eroded away. Here you see a microbial mat chip, right here. It was sitting here originally, but it was ripped off. So it's lying here now as an individual microbial mat chip. Here's another microbial mat chip. It was situated on the surface of the microbial mat, and this is a modern counterexample. This is a microbial mat here. This is the edge of the microbial mat here. This is a fragment, a microbial mat chip, which is exactly the same like this one here, with the difference that this one here is 3.48 billion years old, so much older. Wrinkle structures here in the Dresser Formation. That's from the intertidal zone. You see this irregular folded pattern. That's a modern counterexample here from a modern microbial mat. Then if we cut through a fossil microbial mat chip or a fossil wrinkle structure or something, we see fossil filaments forming a microbial mat texture here. So that those are fossil filaments that are lined by carbonaceous matter. This is heavily silicified here. That's a modern counterpart here. Those dark lines again are the filaments. This whiter material, those are the EPS here, which you can see here as well. then of course we have to do our homework. We have to see, is this really of biological origin? And yes, it is. So here is carbon that has a biological carbon signal. In the lower subpartidal zone, we find polygonal oscillation cracks. As a reminder, this is how they look like in the modern. So here's a polygon, here's a polygon, here is one, and here you can see one of those cracks again. See this crack? It's overgrown by microbial mat again. Here is a rim of a crack, here is a rim of a crack, and here's exactly the same in the Dresser Formation. So here is a crack overgrown by fossil microbial mat. This is the rim of a crack here. This is another rim of a crack. Here is a polygon, here is a polygon, here's another one, and here. And what you see quite nice in this fossil example are those holes that are in the center of some of the polygons, or many. Those holes rise because sometimes under one of those polygons, gas is accumulating, and then a gas dome is forming temporarily. It bursts open, and then we see a hole here in the center of the microbial mat. So it's beautifully preserved here in this lower subpartidal zone in the Dresser Formation. Also in the lower subpartidal zone, the microbial mats show tufts, as they do actually in the modern. So here we look down onto a microbial mat. This is 1 centimeter scale here. We see a honeycomb-shaped arrangement of little ridges, and where those ridges meet, there is a tuft, this little elevated triangle here, pointing towards the observer. Here is a sketch, so this is how this looks like here, and here the same in the fossil, in the Dresser Formation, same pattern, same arrangement of tufts and ridges on those fossil mat surfaces. One last example here in a lagoon in the Dresser Formation is a pile of laminae like this, the whitish color. That is sediment, silicified sand here, which alternates with dark layers, which are microbial mat layers, as we can see here in the modern. That's a microbial mat in Tunisia, about 4 centimeters thick, and you see this alternated bedding, light, dark. We call that a bioluminite. How do we know that this is a fossil bioluminite here in the Dresser? Because we find microbial mat chips, small ones, just a ½ centimeter in size, in those sediments here. So nice, you see it's bended here. The sand is held together by organic matrix. This is a roll up. It's a roll up here, a roll up microbial mat chip. And we took one of those here to see, is this really organic material? And yes, it is. So in conclusion, we can say the Dresser Formation is one of the oldest non-metamorphosed sedimentary units on Earth. It includes an ancient tidal sabkha that corresponds to a modern tidal sabkha in a semi-arid climate zone. The MISS in the Dresser correspond in morphology as well as a spatial distribution to those MISS in a modern sabkha as well. And the similarity in morphology and distribution of MIS suggests that there was already an ecosystem out there, highly diverse and very similar to modern to the modern situation, we have to see, maybe in the future we can say, well, there were perhaps non-sulfur bacteria or cyanobacteria type bacteria, something like that out there. So if you like to learn more about MISS, I wrote a book a few years ago. It's out there, you can buy it, but more importantly, you should read it. It gives a nice introduction into the overall topic of MISS in clastic deposit, ancient to today. And I would like to thank you all for your attention, and I'd like to open the discussion. Thank you.
Great, thank you so much. That was a wonderful presentation, and then now we'll start to take questions. So we already have, can you see me? I don't know if you can see me. Hello?
Me? I see you, yes.
Yes. Okay, just making sure. I can't see myself right now, I don't know why, but so we have a first question from Jacob Boss. Thank you, Nora. You showed an excellent variety of sedimentary structures. Is it possible to link specific structures to specific hydrodynamic conditions and or environments?
Yes, absolutely. So if you think of multidirectional ripple marks or erosional remnants and pockets and so forth, so that's what we did. We went into the modern environment and we really looked where do those structures occur and how do they change in course of 1 year, 2 years, 3 years. So what is actually happening? So first of all, we identified those different latencies that are necessary for specific microbial mat types to establish. So we know exactly epibenthic microbial mats of that type grow in certain zones on a tidal flat, for instance, and it takes them 5-6 months to establish. But then we also take a look at the hydrodynamic situation. Very nicely, that can be done for the multi-directed ripple marks, where we observe first in the spring how a ripple mark field establishes. The ripple marks have all the same direction. And then we were able to observe how microbial mat patches start to evolve. So biofilms start, and of course, where they start to grow within those patches, the ripple marks are overgrown, they are stabilized. That means if there's a storm moving across the area, it reworks those areas where there is not so much biofilm or microbial mat yet. So that means this first storm creates a ripple mark pattern that shows 2 ripple mark directions, and so forth and so forth. Or we measured also how strong has a current actually to be to locally destroy a specific microbial mat type. So for instance, the endomicrobial mats, endobenthic microbial mats withstand erosion 3 to 5 times compared to sterile sand. Epibenthic microbial mats up to 12 times. So they're very, very good sediment stabilizers, and so forth and so forth. So for instance, for the Pongola supergroup, which is another location which is really worth to take a look at, we were able to reconstruct the storm intensity, storm frequency for a certain rock bed, and so forth and so forth. We can measure the distribution of microbial mat chips in an area, including, of course, a fossil site. If we have nicely upper bedding planes preserved somewhere. So we get very clear data on the dynamic, but also on the paleoclimate using the MISS.
Wow, thank you. We have another question from Juan Cui. I'm sorry if I don't pronounce your names correctly, from the University of Paris. They're asking, has MISS been found on Mars or any other planet?
No. So very clearly, the MISS are one of the targets people look at on Mars, because Mars includes a higher volume of clastic material, and a lot of it is aquatically deposited. And of course, there are a lot of how many rovers? 4, I believe, no, 3, 4, taking a look very detailed at outcrops, layer by layer, but until now, the large-scale MISS have not been found. Of course, I wrote a paper some years ago where I described some structures where I said, that could be, but we all have our personal wishes. But very clearly, if we think of mat textures like filaments, microbial mat, like, filaments that interweave or that cause a certain chemical signal in the sediment, something like that is very possible to maybe be preserved on Mars.
Hopefully we maybe find something in the future. Thank
Yep.
you. Next question is from Eva Stuyken from the University of St. Andrews in Scotland. Do you observe a difference between MISS produced by prokaryotes only and those that involve eukaryotes? And if yes, would that difference be preserved in the rock record?
So that's a very, very good question. And I was wondering about that too, simply because if we take a look at the Archean microbial mats, where eukaryotes really, they might have been around. There are nice description of eukaryotes preserved in microbial mats, but very rare. It looks very prokaryotic to me if I take a look at my fossil thin sections. They look the same like the modern microbial mats. So I don't know. So I would say that the eukaryotes, let's say diatoms, which of course come up in Earth history much, much later, I think they're just there. They're really not contributing to the microbial mat buildup itself. I think it's mostly prokaryotic. And of course nowadays, and that's why I said before, from a geological perspective, cyanobacteria are most important in MISS formation because they form those robust microbial mats. They induce those really big MISS. So eukaryotes, I don't think really they have an impact, but the research is done only, let's say 30 years or something. Maybe in the future, people really are able to show differences in morphologies.
Great, thank you. Our next question comes from Steve Kershaw from Brunel University in the UK. Is there any evidence of total abundance of MISS in Archean rocks, when CO2 levels may have been higher compared to the Phanerozoic, which also includes modern times?
I think there's no data set, really. I think, much more needs to be done to really map MISS with respect to frequency. I don't think that the CO2 content plays any role in where those microbial mats formed or where they got preserved, simply because a carbonate precipitation does not play any role in their formation.
Great, thank you. We have another question from Maurice Tucker. Nice talk. You just used the word sabkha. Are there any relics of evaporites there? If not, I would not use the word sabkha. Then maybe it would be a tidal flat.
Yeah, so the dresser formation includes a lot of evaporites, different types, if you are in the field, you see them all over the place. So I think word sabkha is, it's justified, but again, there's clearly a tidal influence there. So we agreed, well, it's a tidal sabkha, very similar like those we see, for instance, in Tunisia, where we have, modern counterparts of MISS as they occur in the dresser formation. But I have really, if someone says, well, those are tidal flats, it's not really a sabkha, I'm fine with that.
Okay, thank you. We have another question from Olaf Alaiki from Freiburg University in Germany. Is there any chance to distinguish between marine and non-marine origins of MISS, maybe by special textures or structures, geochemistry, etc., what have you?
So as far as I know, really not. So if you investigate MISS, you always have to take a look at the Paleoenvironment. That's crucial. I have seen very characteristic MISS, like desiccation cracks, and of course mud chips are all over the place along rivers, very, very typical. Things like multi-directional ripple marks you really wouldn't expect along a, in a floodplain. Might be, might be that someone finds them somewhere at some point. So I would say, because the structures really rise from interaction between physical sediment dynamic and biology, that in theory, all morphologies could form wherever you have sand and moving water. That's what you need: sand, moving water, and a biofilm. And that's provided by any aqueous environment.
Great, thank you. We have a question from Valentine from Oslo, Norway. Bouncing on Jaco's question, can you identify the tidal regime of any micro, meso, or macro tidal areas using MISS?
Yeah, we can. So that's actually something that can be done quite nicely, and we've done that for the Pongola supergroup actually. So if you take a look at the erosional remnants and pockets, it really depends on how the morphology looks like. So what is the difference between the erosional pockets and the height of the erosional remnants? So if you have high heights, the tidal range must have been much higher. Commonly, also the microbial mats are thicker, so that would mean we are a little bit higher in the tidal flat, not really in the intertidal zone where we have erosion remnants and pockets, but the morphology really becomes less and less and less distinct.
Interesting, thank you. We have another question from Sangeeta from IIT Bombay, India. I was wondering, oh, first she says, thank you, Nora, for such an interesting talk and the amazing illustrations. I was wondering if such structures might be possible to see in fluvial and continental areas, microbial settings in ancient rock deposits. I have observed certain microbial structures from the late Triassic rocks of Gondwana deposit in India, but it was very difficult to establish them just from thin sections.
Yeah, so definitely. I know that Nathan Sheldon, he described fluvial MISS. Ugo Beraldi, he described some. Paul Knuth from Arizona, he described some. So they are definitely around. Oh yeah, absolutely. Mm-hmm.
Great, thank you. I hope that answers your question. And then we have another question from Marcello, I'm sorry if I mispronounced that, from the University of Bremen. Very nice talk, Nora. Within the Dresser Formation, do you see specific intervals with MISS, or are they present? Oops, sorry, I just lost my place. Are they present in the entire stratigraphy? And is the depositional setting changing throughout time?
So the Dresser Formation, where we were just studying a small part of it. So that part looks, I'm right now trying to think, which is always a good thing, right? We didn't see any change in the Paleoenvironment for that location. We studied specifically several rock successions, and in total, the rock succession has 46 meters, so it's very short. That all looked pretty much the same. Maybe there was some variation in water depth, so sometimes we were a little bit higher in the intertidal flats, a little bit lower. So I would not see there is much change, and all the MISS we saw, all were where they actually are expected. So let's say erosion remnants and pockets belong in the lower subpretidal zone in the modern, and we found them in the Dresser Formation also exactly there, and so forth and so forth. So that was all very as it should be. Was this the question? Did I catch everything?
I think so. And I think that was our last question. We have just congratulatory from John Reimer in Daran. Thank you very much for the nice talk. And with that, we'll have our closing now. Thank you everyone to join from all across the globe. You had great questions, and thank you very much to Dr. Noranovsky for taking the time to participate in the SEDS online webinar. Again, thank you to the sponsorship from IAS for having these webinars and being able to do them all free of charge. So if you want to join us, next week's seminar is at the regular time, 4 p.m. on the UK time, when Sam Purkis will be talking about carbonates in the Bahamas, and we hope to see you all there. Thank you so much.
Thank you.